Hello everyone. First of all, I'd like to say sorry because my English is a little rusty and I will make some mistakes during the presentation. This is the presentation of the paper Adaptive Clustering of Codes for Assessment in Introductory Programming Courses. My name is Alexandre Barbosa and I am adjuncted teacher at Federal University of Alagoas and PhD student at Federal University of Campina Grande. Evandro Costa and Patrick Brito are my advisors. This presentation is about a quasi-experiment related with my PhD research. The topics of the presentation are the description of the context and the problem investigated, some related works that focus on similar problems, the description of the quasi-experiment related to the adaptive clustering of codes, and finally the conclusions and further work. Programming is one of the basic competencies in computer science. Generally, there are lots of disciplines that focus on the study of algorithms in different perspectives. At introductory programming disciplines, it's easy to find some students that have problems, unmotivated students, some students that have unsolved doubts, and so on. Even the students that are approved in these disciplines have some lack of competence, as stated by the literature. Scientific literature describes lots of possible factors related to the described scenario. We believe that if the teacher could help the students in an individualized way, some of the problems will be minimized or even disappear. On introductory programming disciplines, practical coding activities are adopted. On these activities, typically the teacher selects a set of problems we can call exercise, and the students must implement a code using a programming language to solve the problem. But the assessment of the proposed solutions is quite difficult because of a lot of reasons. The number of students in the discipline, the number of exercise, the number of solutions, the codes or submissions, and possibly the number of solutions that can be sent by students. Another factor is the different types of observations that a teacher can do to assess the codes. He can compare the inputs and the generated outputs. He can observe the code structure if it has the statements that is expected to solve the problem. He can analyze the efficiency of the algorithm and so on. This way we can say the assessment on the described context is a time consuming task, and it's subject to the bias and the errors of each evaluator. So the students in general have to wait a long time to receive the feedback, and feedback has extreme importance to enable learning of any concept, as stated by literature. Some researches already focus on similar problems. One approach, the most used one, is based on online judges. These are systems where a code must pass in a set of tests to be considered correct. If the code fails in one of the tests, it is considered wrong. Generally, the systems classify the solutions in totally wrong or totally right. Some of the systems, online judges, have hints to help the student, but it's not so common. Another set of works, we can say we can describe them as analysis of similarities. Generally, these similarities are used to detect plagiarism, but some researchers focus on other tasks. As example, the analysis of similarities can be used to improve the code considering software engineering principles. Sorry. And there are works that cluster or classify the codes using different techniques, generally using artificial intelligence techniques to help the students and teachers in learning environments. All the works known by me until now use approaches where it seems that all evaluators have the same criterias, and I think it's quite natural to think that evaluators can have different criterias to assess the codes. To understand the research, we need some background. The background is related to the Cummings clustering, to the concept of software metrics. The Cummings clustering algorithms works like this. We can see here at image A the original set of data. All the dots can be considered as the codes. And then first, k centroids. This number k is one parameter of the algorithm. K centroids are defined. It can be defined at random. On image B, we have two centroids, the red one and the blue one. The algorithm computes the distance of each point to the centroid using a set of data extracted from each element, and then it computes the distance to classified element to be considered on a cluster based on this distance to the centroid. On image C, we can see a red cluster and a blue cluster. This is a iterative approach, and the iterations continue until the centroids are not altered anymore. In image D, we can see the final clusters. Software metrics are properties extracted from codes. There are lots of metrics described by software engineering. For example, we can use the number of lines in a code. We can use the number of operators in the algorithm or the operands and so on. In this research, we use some similarity metrics too. In order to evaluate the proposed approach, we use two measures: the Euclidean distance, that measures the distance of 2 points in a n-dimensional space, and the Cohen's kappa, that measures the degree of agreement between two lists of classifications beyond what would be expected at random. Imagine that if I, as a teacher, and I have to assign a grade to a set of exams, I have a teacher assistant and I ask him or her to assign the grades to the same set of exams. But we use dices to assign these grades. This way, the agreement between me and my teacher assistant will be expected to be at random. And if we assign the grades using our criterias, we should have a different degree of agreement. That is what Cohen's-Kappa measures. The agreement can be interpreted as shown in table 1. When the value of Cohen's-Kappa is between 0 and 0.2, we can interpret it as a slight agreement. In the next interval, we can interpret it. It can be interpreted as a fair agreement, and so on. When the value is 1, we can interpret as a perfect agreement. The main idea of the proposed adaptive clustering of codes is like this. The dots are codes. The position of these codes in this axis is determined by a vector of properties. There are software metrics, and we use it to cluster the codes. In the image we have blue cluster, yellow cluster, and a green cluster. So we select one element to represent the cluster, evaluate this element, and generalize the evaluation to all other elements in the cluster. So this way I can have a large set of submissions, but I won't have to assess all of them. In this example, as we have 3 clusters, the blue, the yellow, and the green, I can assess on only 3 codes and generalize the assessment to all other elements at the cluster. We use this and made some measurements using the metrics described. This is just a example. On the best results we found, there were needed 10 assessment, 10 codes need to be assessed, need to be evaluated to get the results we will show. This with 3 clusters is just a description. The clustering approach have 4 steps: the code matrix extraction, the identification of the criteria adopted by the specialists, the clustering generation, and the step of evaluation by the specialists. But the steps 2, 3, and 4 are not executed in a linear way. The step 2, the identification of criteria, depends on the other 2 steps. The step 1, the code matrix extraction, is just to extract and create the vector of properties for each element. The metrics of software engineering are used, and we extract these metrics for each code. But there is 2 kinds of metrics. The metrics that are restricted to the code, example, the number of operators used in the algorithm, the number of lines of a code, it's restricted just to the code. And there are similarity metrics that consider the relation of one code and the reference solutions. This step can be done when the students send the code as a solution to a problem. All the metrics can be extracted. The step 2, to perform the identification of the criteria adopted by the specialist. Well, this step depends on the next steps. What we do, we generate all the possible combination of metrics. These will be used to create all possible set of clusters, and then the specialist grades 10 codes. These grades are used to select the best set of clusters. this is a brute force method. It's not efficient. The step 3, sorry, the step 3, the clustering generation, we are using k-means with k equal to 10, so there will be 10 clusters, and the k-means is based on the set of metrics. We generate all the possible combination of metrics and then generate all the possible sets of clusters. Someone can ask why k equal to 10. We want to minimize the quantity of assessments by at least half. One of the next slides we will show the quantity of submissions for each problem, so that thing I just said will be, I think, will be clearer. Step 4, the evaluation. As said on previous slides, one specialist is needed to assign 10 grades to the clusters, 1 grade for each of the clusters. Then one set of clusters is selected, the one that corresponds to the best fit with that grades given by the specialist. And then for each cluster in the set that was selected, we generalize all the grade to all the other elements. After doing these steps, we need to evaluate the clustering approach. To do that, we used the dataset that have a set of programming problems, a set of codes, and a set of evaluations. The set of programming problems we can call exercises. We used have 6 problems. The first problem name is salary bonus. The second problem name is points distance. These problems were classified as basic problems because the students only have to use simple operators, input and output statements. Student situation and elections were other 2 problems. They were classified as decision problems because the students, to solve these problems, have to use conditional statements as if, elif, else statements. And the odd loop and divisible by 3 were classified as loop problems. All the problems have text descriptions. In the image we show the student situation problem description. These descriptions were the students and the specialists have access to these descriptions. The set of codes that was submitted by the students is described here. Salary bonus has 32 submissions. Points distance has 23 submissions. Student situation 43. Elections 40. Odd loop 41. And divisible by 3 44 submissions. All the submissions, all the codes were written in Python version 2 or 3. This illustrates the k equal to 10. 10 assessments were needed, and half of the assessment that could be done. If a specialist would do 23 assessments, using the approach we are proposing, they only have to make half of the assessment, 10, to get a close list of grades than it was expected if he assessed all the submissions. The evaluations were grades varying from 0 to 10, provided by specialists. We called specialist teachers, and teacher assistants. There were other information the specialists can have to give. The description of the criteria that was used, and a textual feedback that was used. Here we can see one example of a file and the grade that were given to this file, and the textual feedback related to this file. This criteria is related to the problem. When the specialist was assessing the codes, he said he would use these criterias. Anytime he can edit the textual feedback and the grade. On this quasi-experiment, only the grades were used. We have other results related to the textual feedback, but these are more recent and are not part of the paper that was published on ITS. So to evaluate the approach, we compute Cohen's kappa in two ways. We compute Cohen's kappa considering each pair of specialist list versus another specialist list, and we compute Cohen's kappa to a specialist list against the list generated by the clustering approach. We did the same with Euclidean distance. So the results we have with Cohen's kappa vary from 1, the maximum, it's a perfect agreement, to a minimum 0.39. Considering the mean, we have a strong agreement between the generated lists and the specialists. Or we can say the specialists have a little mistake here, strong. The specialists have a strong agreement with the cluster generated list of grades. We can state this with this value of kappa. And the Euclidean distance, we have a maximum of 19.55, a minimum of 0, and a mean of 5.95. We can interpret the list of grades as point coordinates in a n-dimensional space. So we compute this metric to compare the results problem by problem. We can compare if in one exercise the approach were more precise than others. But we saw that this measure was not so good to this. In a more recent analysis, we replaced the Euclidean distance by the total sum of difference of grades, and then we have a better metric, a better comparison. This box plot resumes the results. We have the results related to the clustering approach here at the left of the image, and each specialist, the results are shown in relation to the other specialists. This way we have specialist 1 agreement with all the other specialists, specialist 5 agreement with all the other specialists, and so on. And here we have the clustering approach agreement in relation to all the human specialists. The number of specialists we can see is not linear, is not sequential, because some of the specialists didn't assess all the codes. We have to select only the specialists that made assessment for at least all the submissions for one problem. So this box plot, we can see the clustering approach, minimum values are represented here by the red line. The minimum values obtained by the clustering approach agreement in relation to all the specialists is better than almost all the agreement between human specialists. Only specialists 9 and 10 have a maximum agreement that is better, that is best than the minimum agreement of the clustering approach. So the clustering approach, we can say the clustering approach have a better agreement with a human specialist than human specialist with another human specialists. The conclusions, we have proposed the use of a clustering algorithm to minimize the effort related to the evaluation of codes in introductory programming courses. And the results that we found on this quasi-experiment suggest that it's possible to minimize the evaluation effort. We found a strong agreement between specialists and the cluster approach. And this strong agreement is higher than the agreement between specialists. This research is ongoing work, and much more investigation is still necessary. We can compare different clustering techniques. We can use a larger set of metrics. We can check if the generation of textual feedback can be done with the same approach as proposed for the grades. And this is a quasi experiment. There were no random assignment for the specialists or the problems or the codes. We must check if the results obtained are the same in a more controlled environment, in a real experiment. Some of the references used in the presentation, I kept the number that I used in the textual version of the paper. Some other references, and thanks for your attention.